Assalamualaikum warahmatullahi ta'ala wabarakatuh and salam sejahtera. Okay, in today's video session we're going to discuss about the last topic of this syllabus, which is known as wave propagations. Okay, so therefore I'm going to straight away discussing about this issue, propagation of wave. And for those who have the textbook, you can refer to chapter 10, page number 482. I think the complete chapter, which is chapter 10, does discuss about the issue regarding propagation of wave. Okay, so before I'm going to discuss about this issue, we're going to talk about Maxwell equations. So as what we have seen before, Maxwell equations, there are four. Okay, so let's recall Maxwell equations. So Maxwell equations. Okay, what are they? So the first one we're going to state as the curl of E equal to minus dB over dt. And we have seen this equation being discussed under the category of Faraday's law. So let's denote that as equation number 1. The second Maxwell equation that we have seen based on previous discussion, the curl of H equal to J plus dd over dt. Okay, that should be equation number 2. And we know that the J here have different meaning. For example, the first term of on the right hand side, the J here is known as conduction current density, whereby the second term here is known as displacement current density. So the third equation of Maxwell we denote as divergence of D equal to rho V. That will be known as equation number 3. And finally, divergence of B is equal to 0, denoted as equation number 4. Okay, so this is a Maxwell equation, and we can straightly conclude here these four Maxwell equations are known as fundamental equation in the world of electrical engineering. Why? Because we can utilize these four equations to explain about various applications in the world of electrical engineering. For example, what we're going to talk today, the propagation of wave, we can prove later on this issue can be explained clearly by utilizing this Maxwell equation. Okay, so let's talk about the propagation of waves. So now we can relate the idea that we're going to talk here to the world of communications. Okay, so let's talk about communications. And we know this is very important concept, because with the current situation that we are having now, it plays a very important role to help us going through the difficulties that we are facing now. For example, having a lecture online. Okay, we don't see each other face to face, but yet we be able to continue with our education. How we be able to do it? Because the support of strong communication network. Okay, so when you talk about communications, there are three basic components. First, going to be the transmitter block diagram. Then we're going to have what is known as channel. And then we have going to have the third important block diagram, which is known as receiver. So these are three important block diagrams in the field of communications. So what we're going to talk here we're going to learn how we're going to simulate, okay, the field that propagates from the transmitter to the receiver. That's what our objective now. Yeah? How be able to visualize this unseen world, which is that what we are going to do. We're going to develop the model to represent this scenario. What is it? Electromagnetic wave propagating from transmitter to the receiver through a medium. Okay, so we're going to put a word here, important word we have seen before, medium. Okay, so now we have seen before when we talk about medium, there are various types of medium that we have discussed. For example, perfect dielectric, lossy dielectric, what else? Good conductor and bad conductor. So therefore, by seeing various medium going to have different properties of electromagnetic wave. Yeah? So meaning that when you talk about conductor medium, the way this electromagnetic wave propagate going to be different when you compare to the, let's say, perfect dielectric. So that is what we have to be concerned, meaning that the model that we're going to develop here is not straightforward. It's very dependable on the medium type that we are going to, that we have learned. So in order to make the learning process simple, because what we have seen here, there are very diverse conditions that can be put forward in this argument. So what we're going to do here, we're going to simplify the model. So our concern now, we're going to simplify. Okay, so we're going to simplify our model. Okay, so how? So I'm going to propose now assumptions. So assumption number 1. So based on the topic medium, we're going to assume the medium here either perfect dielectric or sometimes we can also state as free space. So that should be the first assumption that we must make in order to make the model that we're going to develop here simple, which is to assume the medium that we're going to state exists in this discussion is going to be either perfect dielectric or free space. Okay, how we know it? By looking at the loss tangent, sigma over omega epsilon should be equal to what? Equal to 0. Why? Because sigma, which is known as the conductivity, is equal to 0. That should be our first recommendation in our model. Okay, so and then the second issue that we always have to look into in communication system is the noise. Okay, so when signal transmitted from transmitter to the receiver, they always have noise, okay, being included in the signal. So therefore, the noise always a parasitic factor in our model. So we don't want the noise to appear in this particular model, because why? We're going to make our model simple. Okay, so therefore we're going to put forward the second assumptions. Assumption number 2, system contain no noise. Okay, so therefore what is meant by that? The noise actually appear in this channel due to the existence of charge. Usually when you have charge in a channel, that charge will insert a noise known as popcorn noise to the transmitted signal. So therefore we don't want that noise to appear in our model. We're going to state now rho v which is the symbol representing charge, is equal to 0. Okay, so therefore, that's what we should put forward. Why? Because we want to make our model as simple as possible, since it's going to be our first model relating with how wave propagate in a medium. Okay, so due to these two assumptions, what happened to our Maxwell equations? Okay, our first Maxwell equation is going to be altered. How is going to? Because, so equation number 1 will be as it is. However, equation number 2 is going to be changed. Why? Because we know the J here is conduction current density, and based on Ohm's law point form, the J is equal to sigma E. Since conductivity is equal to 0, therefore this term will be also equal to 0, and we end with new equation. We state that the curl of H now can be written as d over dt, and we're going to denote that as our equation number 5. We don't have any more equation number 2. The equation number 2 now has been changed into equation number 5 in order to fulfill the assumption of number 1 and number 2 that we put forward before. And similarly for equation number 3, it need to be changed, and now it becomes divergence of D will be equal to 0. So this is equation number 6. So now we're going to work with new set of Maxwell equation. What are they? Equation number 1, still as it is. Now equation number 5, equation number 6, and equation number 4 as it is. Yeah? So therefore, these are our 4 new Maxwell equations that we're going to use as the fundamental to develop the model of wave propagating in a medium known as perfect dielectric or free space. Okay, so that's what we're going to continue here. So now, so we are saying now, okay, this is our transmitter. I'm going to put nice antenna here, and this is our receiver. So now we're going to model this wave, and we can't see this wave yet, we assume it to be there, and this wave is known as electromagnetic wave, correct? Why? Because the source that we use to generate these waves usually AC current. So therefore, that's what going to be our wave propagating in the medium. And from our discussion that we heard before, whenever you have electromagnetic wave, you will have 2 different components of field, which known as electric field. At the same time, we're going to have as well magnetic field. Okay, so what I'm going to do here, I'm going to propose a method that we're going to develop the model of this field. Okay, we're going to call this as our electric field, and then we're also going to develop our magnetic field. So what we're going to have at the end of this discussion, equation representing E as well as H that are propagating in this medium. Okay, that should be our objective here, to develop equation of field that we can use to represent the model of E and H in this particular conditions. Okay, so let's now focus on electric field. Okay, so let's do electric field now. So we're going to focus on electric field. Okay, we ignore magnetic field now, just focusing on electric. So how are we able to develop equation of electric field in this situation. Okay, so now we can see why Maxwell is important. The way we're going to develop the electric field model by referring to Maxwell equations. And from Maxwell equation that we have developed earlier, there are 4 set of equations. So we're going to use this equation in order to develop equation for electric field. So from 1, I'm going to use equation number 1. Okay, from 1 now. Okay. Okay, this is why you see Maxwell is very important. So let's curl the left hand side of the equation. Okay, curl of E. So if I curl the left hand side of the Maxwell equation number 1, I must also do the same thing to the right hand side. Curl. So minus. So what medium that we're having here? Dielectric. So mu dH over dt. Okay, that should be what we're going to do. Why we're going to have an equation only containing electric field? As what we can see from this equation, equation number 1, it contains electric field and magnetic field, whereby equation number 5, it contains magnetic field and electric field. We don't have any equation that only involve one field, which is electric field. So that's why we have to manipulate. How we manipulate it? By doing this mathematics. So if you do this mathematics, the left hand side equation now can be extended to become this equation: grad divergence of E minus del square E. Okay, so this one should be simplified to become minus mu d over dt curl of H. Okay, so let's simplify further this equation. So if I'm referring to equation number 6, up here, I can see divergence of D equal to 0, correct? So we know D is equal to epsilon E. Therefore, we can also state that divergence of E equal to 0. And when we refer to our equation here, this term can be equal to 0. Why? The reason because equation number 6. Similarly, if I refer to this bracket term here, I can refer to equation number 5. Okay, equation number 5. The curl of H equal to dd over dt. So I can replace now this term with dd over dt. Or in other words, our displacement current density. So what we're going to end here, we're going to end with the special equations. Negative and negative will cancel each other. What we're going to have, del square E going to be equal to mu epsilon d square E over dt square. You see, all the equations that appear in this equation only containing electric field. That's what we want. Because why? We want to model electric field. So it's very important to develop equation that only containing electric field. Alhamdulillah, we have done so. So this is what you need to do. You use Maxwell equation as your fundamental reference equation, manipulate it to your reasoning, then you're going to have what you want in this. What you want, the equation only containing the information of electric field. So this equation, we call it to be known as wave equations. Okay, whenever we talk about wave, the equation must have this kind of pattern, regardless where the wave is actually propagating, either in optical fiber, in a waveguide, in microstrip, in the air. Whenever you have wave So that wave equation can be represented by this simple equation, and sometimes we call it to be Helmholtz equation. Okay. Okay, so now, alhamdulillah, we have completed a set of equations representing our E. And then what we need to do, logically, we also need to set an equation that representing our H. And then if you use the same method that shown here, I'm sure you can prove to yourself that the H can also be represented with the same wave equation equal to mu epsilon d square H over dt square. Okay, so in order to prove this equation, I believe you can do it yourself by using the same step that I've shown you before. Yeah, so what is important for us at this junction, we need to develop an equation come from Maxwell, and the equation only contain the relevant field of analysis, and then that's what we need to have at this junction. So now I'm going to continue. Okay, so I'm going to use a new space. Okay, so we are still in the world of electric field. I'm going to remind myself by saying electric field. Okay, so this is what, so we end with this equation, wave equations equal to minus mu d square E over dt square. Okay, so we have to continue. We want to develop equation representing our electric field. So what we have to refer now, again, the important condition we put forward just now, our model should be simple. So therefore, I'm going to put my third assumption now. Assumption number 3. Okay, we are dealing with plane wave model. Plane wave model. What does it mean? So it means that this is your antenna. Okay, in communication, we want the signal to be able to propagate very far. Okay, so when you have a position that which is very far from the antenna, so that position allow the wave to emulate what is known as plane wave. Okay, if you analyze the wave close to the antenna, so the shape of your antenna will have influence in your generated field. For example, if you have an antenna appear to be a straight line, so you have to use what is known as cylindrical coordinate to analyze the field of propagation, whereby if your antenna appear to be as a dot, so you have to use spherical coordinate as the model of mathematics to analyze the field, since the distance here is very, very far. Okay, very far. So this particular wave going to emulate what is known as plane wave model. Why is very important? Because when you assume your model to be plane wave, so therefore by default the only coordinate that we're going to use in this analysis is going to be Cartesian coordinate. So why we always assume our coordinate to be Cartesian? Yes, to make the model simple. Okay, if you analyze in terms of cylindrical coordinate or spherical, for most of us that not familiarized with that type of model, the analysis is going to be a bit cumbersome. So in order to make it simple, since this is your first step in modeling wave, so therefore I'm going to assume the wave that we're going to model known as plane wave. So by default, the coordinate that we're going to use to represent in this model is known as Cartesian model. So what happened to our wave equation? So therefore the wave equation now need to be changed to become this term, d square e over dx square based on Laplacian table, d square e over dy square plus d square e over dz square equal to mu epsilon. Why mu epsilon? Because we are dealing with perfect dielectric, d square e over dt square. So yeah, the model is cumbersome. Why? Because we have to use all the three variables in our model, which are x, y, and z. So why not make it simpler further? How? By only utilizing one field at a time. So how we do it? So by suggesting new assumptions. So assumption number 4. Okay, the electric field is in x component, okay, comma, propagating along z-axis. Okay, that's what should be our next assumption in order to simplify further, to reduce the variable involved in the model from 3, which are x, y, z, into only 1. You can see later on. So what does this statement meant? So let's say you have a scenario like this. So this is a surface of water. Okay, and then let's say there's a floater on the surface, and then let's say the axis represented here is z, and then the axis vertical to it, we call it to be x. So let's say we throw a stone to the water. So what happened? It's going to produce ripple, correct? So this ripple or this wave going to propagate. We throw something into the water, so the ripple are going to be produced by that condition, and then this wave going to move, correct? So when this wave arrive at this floater, what will happen to it? Even though from our observation we going to see this wave move along the z directions, it's moved towards this structure. So whenever this wave arrive at this particular floater, what you're going to see, this going to move only in these directions. You won't see this particular structure move together with the wave. The wave still move along this direction, but yet you see this particular structure only going to change position vertically in x-axis. So what we're going to state here, this field, which is our Ex, is function of z. That's what we mean by that. So meaning that we're going to say that E is in the x component propagating in the z direction. So therefore we're going to observe this structure only going to move in the vertical direction as what we are stated here in the x-axis, but yet whenever we see this wave move, it is moving in this z directions. So with that state, what we're going to see, this general equation going to be simplified further to become what? To become this equation, dEx over dz square equal to mu epsilon dEx over dt square. Okay, so alhamdulillah we able to simplify our wave equation that utilizing plane wave, which is using Cartesian coordinate. Yet we know that the E is an x component propagating in the z-axis. So what we have to do now, we have to solve this problem. We need to solve this to get the solution. Ex equal to what? That's what we need to do next, because we need to solve this problem in order to get the field of electric model in our medium that we stated to propagate from transmitter to receiver. So how are we able to solve this problem? Okay, there are so many methods that you can use in order to solve for the Ex. For me, as usual, I like to use comparison. So this is very typical of me, because I like to compare using other people's work, and then from there I'm going to manipulate a bit to justify in my condition. That's what I always did in my research, because to solve it mathematically, it's cumbersome for me, old man. Maybe young people like you can do it straight away. Double integration both sides by part, etc., and then you're going to get the same solution as inshallah mine. Okay, I'm going to use comparison. So by stating this argument, okay, if my problem given as this term, if the problem is the problem is represented as d square, let's say put g term here, over dx square over 1 over, let's say u squared d square g over dt squared. So that's my general term. So this I'm going to call, therefore, the solutions, in my case now g equal to function of t plus minus x over u. Okay, now you can see, you can use a lot this argument logically. So that's what I'm going to use in my solution, the way I'm going to solve this problem. So let's relate now the general condition to our case now. So what field that we are modeling here? Electric field, correct? And the electric field that we are analyzing here, we always said to be what? Okay, so we always said the field, electric field, to be sinusoidal. Correct? So whenever sinusoidal, how we represent mathematically that condition? Yes, by using E naught exponential j omega t. Remember that term that we stated earlier in my previous video? And this can be represented by saying, based on Euler model mathematics, E naught, and then cos omega t plus j sine omega t. Agreed? And usually in our situation, to make this model simple, we only take the real parts. We state that E is real part of our E naught exponential j omega t. What is it? E naught cos omega t. Okay, so therefore whenever we solve problem based on this simplified assumption, our final solution always deemed to be different than the measured value, because the measured value do have complex value in it, which involve real and imaginary. But usually in the model, to make the analysis simple, we only take the real part. So for those who always said that the measured value equal to the model value, your statement wrong, because you can see from this simple argument, the model will just take the real part, ignoring the imaginary part. Wherever when you measure signals, they have these two conditions together, the real and imaginary. So let's go into back to this issue. So since we said the things to be sinusoidal, so my argument now, the functions are going to emulate this condition, cos term. Okay, that's what I'm going to state now. Okay, using that observation, so now I'm going to solve this mathematics now. So what is our concern? Ex. Okay, that's what we're going to solve now, equal. So that's done. And then we're going to use the cos functions. So whenever you have used cos term in trigonal, you're going to have amplitude. Good. I'm going to denote the amplitude as Ex. Positive. Why I'm going to explain later on. Cos. That have to have this term. T minus. So I'm going to replace this with constant now. Beta over omega. And then directional propagation is what? Okay, you can see here X now becoming Z. That's good. So I'm going to put omega here. Okay, so that is my solution for the first term, the negative term. So I can see there's a positive term there. I have to add again. I'm going to have what now? Ex negative cos omega t plus beta over omega z volt per. So this is our electric field model of the propagation of wave in the dielectric of free space medium. That's how what you need to do. You can see how simple it can be done. So not that difficult. Okay. Good. So now let's talk about this solution further, because simply leave it like this is going to make you all feel frustrated, because just set of equation, what does it mean? Engineer, we always have to know what does it mean. It's not equation per se. You can develop complex equation, but if you cannot explain it, what for? Because we engineer, not mathematician, we must be able to explain. Okay, for those who just can produce big equation but cannot explain, then use a computer to model it, I think that's what lacking in our current engineers. So we're good in using computer tools, but unable to explain why. So that's what I observe from a lot of PhD students, try to explain their work. So let's explain these simple equations. So let's say you have a string, okay, a string, guitar string, for example. So this is what I'm going to explain, guitar string. So let's say that this string is aligned to the z-axis. So how you make the string produce sound, we have to plug it. So when we plug it, what we're going to produce? Wave. So the wave going to move, let's say, in these directions. So when this wave arrives at the end of this string, what happened to the wave? It's going to be reflected back. Okay, it's going to be reflected back in these directions. So this is actually what you're going to have. The wave moving along the string in such complex manner. So at any point on the string, what we can see, there are two dominant field components, the blue component, number 1, and the red component, number 2. And we can see from this diagram, this wave moving in opposite direction. One moving along the z, another one moving opposite to z. So let's relate that to our equations. So what we have here, equations. So I can see the two terms, so logically now is related to the two wave component in our guitar string. So which one belong to which? So let's look into it. So what is important here, whenever I see the variable appear here, that variable indicate to me the axis of propagation. So what axis is our wave is propagating? Yes, z-axis. That's why you're going to have z here and z. So we know that both wave propagating along the z-axis. So the second important thing that we must observe the sign. Okay, the sign involved here. So whenever I see negative sign here, that indicate to me the direction of propagations. Okay, we agree that the wave propagate along the Z, but the direction is what? Is it positive or negative? So whenever you see negative here, so you can conclude the wave is moving in positive Z directions. That's how you state. And this wave now, because it's positive now, so these two information will make you make a conclusion that this second term moving in the negative Z directions. So in other words, what you can conclude, the first term representing our component number 1 moving in these directions, and then the second term here moving in negative Z direction. We've agreed with this red color. So what is said in this solution, the E contain two combination of wave 1 plus wave number 2. So that should be our general equation of wave of E in the medium of interest now. And then what we can see here, just amplitude. No need for me to explain. You can relate that to what you have learned before. Okay, and then for the beta omega, I'm going to explain later on in my video. I'm going to just at this moment explaining about what the meaning of the solution that we are having here. What we have here, electric field model of wave propagating in the model that we are developing here, containing two components. How we determine that component by looking at the detailed information in the equations. So that's done. Okay, what should be done next, you think? Okay. Okay, so we, alhamdulillah, at this junction, managed to find the solution for the E field. Okay, that's done, alhamdulillah. So we know that electromagnetic field contain electric field as well as magnetic field. So what to be done here, we need to find the corresponding magnetic field. So this is typical EMT problem. When you been asked in your final exam, we will give you one field. You need to find the corresponding field. For in this case, we know the electric field. We need to find the magnetic field. So that's what we're going to do here. How to determine the corresponding magnetic field. Okay, so how we do it? So, good. Those who answer my question, refer to Maxwell Equation. That's good solutions. Okay, so we have 4 Maxwell equations. Let's rewrite those equations. The first one, the curl of E equal to minus dB over dt. We call it equation number 1. And the second Maxwell equation that we have simplified, the curl of H equal to dd over dt. We denote this to be equation number 5, remember? Okay, these two equations are relevant to our discussion here. Why? Knowing E, we can find H. Knowing E, we can find H. You can use either Maxwell equation, either number 1 or number 5, doesn't matter. Because we can see, knowing the electric field, we'll be able to find the corresponding magnetic field. So what I'm going to do now, I'm going to use equation number 1. Okay, for those who want to check my work, you can do it by equation number 5. hopefully from your work going to be agreed with mine. Okay, so that's what we can check our work here. So I'm going to use equation 1. So using equation 1. Okay, so I'm going to use equation number 1 where I can see left hand side. Okay, I'm going to have, based on Cartesian coordinate, x directions, y directions, z directions, that's good, and then d over ds, del notation, d over dy, d over dz. Okay, and then what field that we have here? Ex field, ex component. Do we have y component? No. Do we have z component? No. We have ex component only. Yeah? And then doing the mathematics, what we're going to end with going to be x 0 minus 0. That should be minus y. Okay, close to y. Going to be 0 minus d ex over d dz plus z 0 minus de x over dy. That should be the simple solution based on the matrix. Okay, let's solve the mathematics. What we're going to see now, okay, for this particular term, you're going to end with 0y because our ex does not contain any y variable. Okay, so we just leave it with what we're going to have, this term now. Okay, that should be our final solutions. Yeah? So we're going to be y dex over d dz. That should be the solution of the left hand side. So let's do the right hand side now. The right hand side. The right hand side going to be equal to, what is it? Okay, minus and then mu d over dt, and then the h going to be what here? Cartesian hx in x direction plus hy in y direction plus hz in z direction. So that should be our general substitution. Yet when we relate to our solution on the left hand side, we're going to say that the hy here, sorry, hx here can be assumed to be 0. Why? Because the x component here is 0. Similarly, on the z term, we're going to state this equal to 0. Because why? The z term of the left hand side equal to 0. So what we're going to left now, the h will be in the y component. See? The e in the x component, the h going to be slightly different. Not in the x component, in the y component. Okay? So that should be the typical pattern you're going to observe based on the plane wave model. Okay, so let's solve the mathematics now. So what we're going to do, I'm going to minus mu dhy over dt. I'm going to ignore the direction, just focus on the amplitude, and then should be equal to, okay, let's see our solution before what we have. We're going to have this. Okay, so we need to do what here? We need to differentiate with respect to z, correct? So let's do that differentiations. So what we're going to have first, we're going to differentiate with respect to z. What we're going to have, we differentiate, so we're going to have ex positive, okay? Differentiate with respect to z, cos will become what? Negative sign, okay? Negative sign, and then you're going to differentiate, okay? So you're going to have negative beta, negative will become beta. So cos omega t minus beta over omega z. Do we agree on that? Okay, and then for this term, I'm going to differentiate, okay, since plus, now I'm going to have negative value here. So ex negative beta cos, no. So this now change into sine, sine, subhanallah, terrible me, sine, and then omega t plus beta over omega z. Okay, so this should be sine, sorry about that, this should be sine. Okay, because we differentiate cos respect to z, we're going to get sine with respect to z. Okay, that's done. Okay, let's continue now. What we're going to have here, we're going to have h. So in order to have h, first I have to move the mu to the right, divided by minus mu. Then I have to integrate with respect to t. So what we're going to have now, hy going to be equal to 1. So negative mu, then when I integrate sine, we're going to give us what? Negative cos, correct? So negative cos with the negative here become positive. So what we're going to have now, ex positive beta over mu omega cos omega t minus beta over omega z. That should be the first solutions. Okay, negative becoming positive, yet we integrate, going to have negative cos. What we're going to have negative here, ex negative beta over mu omega cos omega t plus beta over omega z. Unit here should be ampere per meter. Okay, so that's done. So what we're going to simplify further, we can do that by stated that hy can be written as hy positive. We're going this represented as this term cos omega t minus beta over omega z plus hy negative. We can do that. Yeah, cos omega t plus beta over omega z. So that should be the solution, ampere per meter. Okay, so this should be the corresponding magnetic field. So what is important here in this example, when you are given one field, you can find the corresponding field by using which equation? Maxwell equation. Okay, so from this, what you can see, that can be done mathematically. Yeah? So we have solved the electric field. Now we're going to have the corresponding magnetic field. Okay, so again, what is our objective here? To model the wave of propagation. So what we are doing here, again, I like to highlight again to re-explain. So we have a transmitter, and then there's a receiver very far away. Okay, so what we are doing, we are modeling the plane wave here. So what is the equation of the wave in this particular region, which is very far from the transmitter? And then since we are assuming this to be electromagnetic wave, we know it's contain electric field and it's also contain magnetic field. Alhamdulillah, we just able to prove to ourselves that this field can be developed. And what's important here, this model is utilizing plane wave model. So I'm going to explain about plane wave model more detail now. Okay, so let's recall now. So this is our plane wave model. Okay, based on our effort today, we have solved for electric field. So electric field, okay, we said that in this discussion, Ex, I'm just going to take the positive now, Ex positive, ignoring the other side, cos omega t minus beta over omega z. That should be our solution. Yeah, I'm just focusing on the one direction. So the corresponding magnetic field, we have proof, is Hy. You see, it's no more Hx. Hy equal to Ex positive beta over mu omega cos omega t minus beta over omega z, whereby we can state that this term can be also known as Hy positive. Okay, let's plot this simple wave. So what we have here, so this is, let's say, your E, so this is the direction of propagation, the Z. Let's say that this is the X axis and this is the Y axis. Let's make it like that. So I'm going to draw this to be in red color. So the E in which component? The E is in the X component, so must be aligned to, so I'm going to draw to be, let's say this my E is going to be horizontal field. Okay, so this is our E field. Okay, at the same time, what we're going to observe, the corresponding magnetic field. So the magnetic field is along the X now. So it's going to be vertical component. Okay, so I'm going to make it vertical like this. And for the E, going to be horizontal like this. So you can see now. Okay, so that should be the model. And then the H also propagating in this type. So this is the H field. Okay, so that should be our product of our analysis. We'll be able to develop simple model to represent our field, electromagnetic field propagating in the dielectric or free space. So what I'm going to do now, I'm going to re-summarize the spatial behavior of plane wave. Okay, number one. Okay, electric field and H are orthogonal to each other. The E and H will never be in the same axis. That should be the first thing you must always deduce or conclude whenever you are dealing with plane wave model. The electric field and H will not be in the same axis. For in this case, the E in the X, the H in the Y, orthogonal, 90 degrees to each other. The second thing that you must always observe, they always agree to this simple mathematics. The unit vector of propagation is equal to the unit vector of E crossed with the unit vector of H. Okay, this is unit vector of propagation. This is the unit vector of electric field. This is unit vector of what? Magnetic field. Let's test that. Okay, let's give a try here. So, what is the direction propagation based on this mathematics? Okay, based on this mathematics, we can conclude that both field propagate in which direction? Yes, positive Z. So we said before, E in which component? X component. H in which component? Y component. So you can see this must always be true whenever you are dealing with plane wave model. Okay, so there you are. Okay, so that should be the thing you're going to use whenever you want to solve for corresponding field. So meaning what? Meaning that you can either use the first method that I showed you before, which is utilizing quite detailed or in very tedious manner the actual Maxwell equation, or you can use this standard pattern. Meaning that by knowing electric field, you can find the magnetic field by using these special characteristics. So meaning that you can utilize two methods in order to find the corresponding field in wave propagation, either by using directly wave equation or by using the special behavior of the plane wave model that we are defining here. So what we have to explain now about the parameter involved now. Okay, so what is omega? Okay, so omega, okay, I'm going to put finally now the parameter of wave. So what I mean by that, I can see a lot of symbols that are not that familiarized. So I think omega for us, for most of us, no problem, is angular frequency equal to 2 pi f. That's done. So what is beta? Beta is known as equal to omega mu epsilon. Okay, this is known as phase constant. Okay, so that should be radian per second, the unit. Okay, what else important regarding the wave? The velocity, okay, u equal to omega over beta, or sometimes we can write it as equal to 1 over mu epsilon. So that should be the wave velocity. You can see velocity of electromagnetic wave does depend on the medium, mu and epsilon. So different medium going to allow the electromagnetic wave moving in different speed. So that should be the one. And the last important parameter in the world of propagation is this symbol. Okay, this symbol is known as impedance. Okay, and impedance is actually being defined as the ratio of Ex positive over Hy positive. If you are referring to the equation up here, or if you are referring to set of equation before, negative Ex negative over Hy negative, if you are referring to the reflected wave. So, and then when you do the substitution, actually is equal to mu over epsilon. The unit for this impedance is ohms. So now you can see impedance does depend on the medium. For those who find impedance using resistance and capacitance, this is just a basic method, but actually the final impedance value depending on the material that you're using to fabricate the cable or the transmission line. So because it does relate to the actual how the electric field and the magnetic field are behaving themselves in the medium. So that should be impedance. So there you are. So I think from here we have able to explain to ourselves how actually electromagnetic wave propagate in a medium known as perfect dielectric or free space by utilizing a plane wave model. So I'm going to explain further about this issue by talking about more relevant medium, because in terms of medium, it's not only free space, not only perfect dielectric as what we have known before. Medium can be categorized as a lossy dielectric or conductor. So we like to understand how the electromagnetic wave propagate in such more practical material, because this is just theoretical only, because we make this discussion simple, because to make the understanding of the model easier, because once we embark into more advanced or more complicated material, having this in our background, we inshallah might understand the situation much clearer. So with that, I would like to thank for your attention. Sorry about the very long video session here, but with that, alhamdulillah, thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.